So we're now in a position to write down the transistor equations for this Nmos device. In the next slide we'll write down the equations for the Pmos device. So in the Nmos device we have the source and the drain are N-type materials. This is how we get the name Nmos. Now the charge carriers are electrons, and electrons flow from the low voltage terminal, which is the source, up to the high voltage terminal, which is the drain. So the electron flow is in this direction. But remember, as we said before, the conventional current flow is from the high voltage to the low voltage, which is in this direction. So there's three regions that we're interested in for this device, so three regions of operation. The first is whenever the device is off. So whenever the device is off, there is no inversion layer anywhere in this channel. So we ensure that that's the case whenever the gate source voltage minus Vt is less than or equal to 0. Or equivalently, you could take this Vt over the other side, and we're really just saying that the gate source voltage is less than the inversion, the threshold voltage Vt. So if that voltage is less than Vt, we don't get any inversion on this side of the channel. Now if we don't get any inversion on this side of the channel, we know that this voltage is less than this voltage, so we will not get any inversion over the channel as a whole. Now in that case there, the current flow, that is IDS, is equal to 0. So that's the current from drain to source. Now notice the way that's written. It's written as IDS, not ISD. So IDS is the current from the drain to the source, which is the conventional current. So we're just saying the conventional current is equal to 0. Although remember, in this case, the actual current is generated by electron flow, which is in this direction from the source to the drain. Now the other two regions of operation are determined by the equation that we've seen in the last video. So the first one is the saturation. Now in saturation we say that the gate source voltage minus Vt is less than or equal to VDS. Now in this region here, it means that we have an inversion, but the inversion doesn't take place all the way along the channel. There's going to be a pinch off point somewhere along the channel. But note here that even though there is a pinch off at a particular point in the channel, the carriers still have enough energy to jump across onto the drain. So we still get a current flow, but the current flow is given by this equation here. So the current drain to source, that's the conventional current, is beta n upon 2 VGS minus Vt squared. Now we'll talk about this beta n just in a moment. And we'll also look at the derivation, but it'll just be a heuristic derivation of the current. We won't get into the full details because we don't really need to for the course. Now the other region of operation is the linear region, and that's when our VGS minus Vt is greater than or equal to VDS, and we've seen that in the last video. So in this case here we have an inversion layer across the entire length of this channel. So in that case the current is given by this equation here. IDS is equal to beta n times VGS minus Vt all times VDS minus VDS squared upon 2. Again, we'll have a look at the derivation of this, but again it'll be a heuristic derivation, not a complete derivation. Now another thing to note is that these are first order equations. There are other second order effects. You're going to get parasitic PN junctions and parasitic capacitances and other parasitics that occur, but we're not going to take care of these. We only need to be interested in these first order equations. So these are the three that we're going to be using for this Nmos device. Now we've got a similar set of equations for the Pmos device, so I'll just state those in the next page. So here are the equivalent equations for a Pmos device. So remember, a Pmos device is going to have a P-type source and drain, and the bulk material here is going to be an N-type. Now the charge carriers here are going to be holes, and holes are going to travel from the high voltage side to the low voltage side. So that means that the source here must be the high voltage side. So this is the high voltage side here, and this is the low voltage side here. So the holes are going to travel in this direction here. In this case here, this would be the same direction as the conventional current flow, which is from a high voltage to a low voltage. So if you check out the three equations, you'll see that they're almost identical. The only difference that you're going to have in these equations is the greater than or less than signs are going to be swapped in each of them. And also we've got a minus value here for the current, and this value of beta is a different value because it's the beta value for a Pmos transistor as opposed to the beta value for an Nmos, which we'll get into just in a minute. We'll just talk through the first one here. The cutoff is whenever the device is completely off. Now whenever the device is completely off, it means that there is no inversion layer anywhere along this channel. So in order to ensure that that's the case, if we say that the voltage between the gate and the source is going to be greater than or equal to the threshold voltage Vt, then what we're really saying is the gate source voltage in effect would be the voltage which would be the field running from the gate terminal down to the bulk or the substrate. In which case what would be happening is we would be attracting electrons up towards the more positive side. So this would be, the gate would be the more positive, and the other side of the device here, which I'll actually just draw in, okay, which is the substrate or the bulk connection, would be at a lower voltage. So the field would be from a positive to a minus, and it would be drawing up more and more electrons. As it drew up more and more electrons, this would become more negative. So in effect we would be in a position of accumulation. So we will have accumulated the electrons into this region. So that's going to ensure that no inversion can take place. We'll actually have the opposite of inversion, we have the accumulation. So it means that this device here is going to be cut off. There is no current going to flow. So the current from drain to the source is equal to a value of 0. Now we can look at the saturation and the linear equations, and these are the same as the previous equations, but the greater than equal to has been swapped round about. It's now this one and the previous one would have been less than equal to, it's now greater than equal to, and the same in this instance here. Now the thing to note here is the value for the current, and you can see that there's a negative sign in front of these. And you can see here that this is really just down to the convention about current. We can see here that the current has to come from the source and then it has to go to the drain. So that's how we've defined our device. Now in this case, the Pmos device, the charge carriers are holes. Holes always travel from the positive side to the negative side. So that means that the source in this case here must be a positive value, and the drain must be the negative value. So the whole flow is in this direction here. But remember, in the previous law of equations, we actually defined it in terms of the current drain to source. So that's the drain current minus the current at the drain minus that at the source. So in order to keep these the same, it means that the actual current flow is in this direction from positive to negative, but we've decided to keep it as drain to source, which is this direction. So this direction here is going to be the negative of the current flow, which is from this side here to this side here. So the conventional current flow would have been positive to negative, which is the positive side here to that side here, but we're actually writing it in terms of the current from this side to that side, which is going to be the negative of that conventional current flow. That's how we get the negative sign in here. But everything else is just the same. The types of equations are just the same. Now, it can cause confusion whenever you first start this and you see the different equations and the greater than, less than signs, and you see them mixed up. But as we work through and we start doing examples, we will get used to using them, and there's ways of coping with these complexities to make them a little bit simpler. So that's us finished talking about that Pmos device in terms of the transistor equations. From now on, we'll go back to the Nmos device and we'll describe things in terms of the Nmos device. So we have an Nmos device here, and what we want to do is we want to get away from representing the device in this format here. Now, it was useful to use this format in order to work out the device physics and the current flow and the type of current flow and where the current was flowing to and from, and working out inversion layers, accumulation and depletion. But now that we've gone through this low level description of the device, we're wanting to come up to a more high level description, and this is the device symbol that we really want to use from now on. Now, we've got here the Nmos device, and we know that this device here, we're going to have the positive terminal here, and we're going to have the low voltage terminal here. So we'll just put a value for minus here. The minus just means that this voltage here is at a lower potential than this voltage here. So we know that this here is the conventional current flow. So we've got the conventional current flow of this device in the y-axis here, if you like. So that's the current from the drain to the source, current from the drain to the source through the device, which is in this direction. But of course, we know from our work and what we've done previously, this is the Nmos device. The actual current is carried by electrons which travel in this direction. So the actual current, the actual electron flow is in this direction here. Again, this is just an historical anomaly. So now, if we were to put the drain source voltage along this axis here, so this is going to be the voltage from the drain to the source. Then we could draw out the characteristic for this device, and the characteristic would look like this. So we would have the linear region here. Now the linear region we know occurs when VGS minus VT is greater than or equal to VDS. And the saturation region here occurs when VGS minus VT is less than or equal to VDS. Now you'll notice here we've got less than equal to, greater than equal to, and it doesn't really matter the fact that these mathematically don't look correct. One would have to have the less than sign, the equal to sign missing, but that doesn't matter for our purposes here, because the transition between these two is a continuous transition, and you can see that continuous transition here. Now you'll notice that the point up from here is called the saturation. So really what that's telling us is that beyond a certain voltage, the VDS, it doesn't matter how much we increase that voltage, we won't get any more current flowing through this device. So in effect, this is the pinch off region. So the device is going to be pinched off, and it doesn't matter how much we try to increase this drain source voltage, it won't affect the drain source current. Now, it's not exactly correct. There are second order effects that occur, so this line here doesn't actually sit straight like this. It'll actually sit up at a particular angle, okay? So it will have a gradient associated with it, but that's a second order effect, and we're not interested in that for this course. Now the other region here is called the linear region. It's called linear because as we change the drain source voltage here, the current here from the drain to the source increases in a fashion that looks almost linear. So that's a straight line here. But it's not exactly right because this is the current equation for it here. And you can see here there's actually a squared term in for this voltage VDS. So that isn't exactly linear, although in this instance here we just call it the linear equation. So you can actually see this transitioning from the linear to the saturation, and this transition point is going to be given by this point here. So that's going to be VDS is equal to VGS minus VT. So you can see that that's the case because if we take this, and I'll leave this as an exercise for you, you can take this equation here and you can put it into the linear equation here. So this VDS will now be replaced by VGS minus VT. So that would then give us the VGS minus VT all squared. And you can see here that we've actually got the VGS minus VT all squared up here. Of course, we still have this factor here, but we're just ignoring this for the moment. So you can see that there's a continuous or a smooth transition from linear to saturation. And that's hardly surprising, is it? Because we're just looking at the transition between the inversion layer passing over the entire channel or it being pinched at some point along the channel. Another thing to note here is that we could have the device turned on, but if we don't have any voltage between the drain and the source, that there's no difference in the voltage between these 2 points, then we won't get any current flowing in the device, and that's really what we see here. Whenever the voltage between drain and the source goes all the way to 0 volts, you can see here that there's no current flowing in the device. The device is still on, but there is no current flowing through it. So that's all there is for this video. In the next video we'll go on and we'll look at some of the parameters that we've got access and we can change in order to do our designs, and we'll also have a look at the threshold voltages for different types of devices. So thank you for listening. I'll get you in the next video. Goodbye.